Let's examine the Python code to gain a better understanding of entropy and cross-entropy. The variable p represents a probability distribution. The variables q1 to q4 are distributions that bear decreasing similarities to p. Calculating cross-entropy in this manner involves a significant amount of typing, but is beneficial for grasping the concept. Please note that the logarithm of 0 is undefined. In our case, we consider 0 probability as approaching 0 from the positive side. Therefore, according to L'Hopital's rule, 0 multiplied by log 0 equals 0. Please note that we take the logarithm base 2 for the calculations. We also calculate the cross-entropy values with the natural logarithm log. We can compute the cross-entropy more easily by defining a function. You can pause the video to review the function. PyTorch provide a function for calculation of cross-entropy. However, we got different results. Before we answer the question why it was that, let's define a softmax function. Pause the video for details. Let's define inputs to our softmax function, and convert these input into probability distributions, named q1 to q4. The cross-entropy values are calculated between p and q. Now we calculate the cross-entropy using p and l instead of q. This time, the result agrees. In PyTorch, the one-hot label, p, can be represented by the index of the hot position. The cross-entropy function accepts this index representation as input and achieves the same results. The average value is calculated. We stack L1 through L4 into a new tensor named L. Each target has the index 0 as the hotspot position. The cross-entropy is then calculated using the PyTorch function, cross-entropy, resulting in the average of the cross-entropy values from the 4 samples. What lesson do we learn from the above code? Logits are the raw outputs of a neural network, before the activation function is applied. The softmax function is commonly used in neural networks for classification tasks, to convert the logits into probabilities. Logits are also known as raw output scores in some contexts. For multi-label classification, cross-entropy is commonly used as a loss function. The PyTorch function that calculates cross-entropy takes logits as inputs. It is reasonable to assume that the PyTorch function combines softmax and regular cross-entropy. PyTorch offers a function called NLL, negative log likelihood, which seems to be the regular cross-entropy function. To expedite the process, I inquired with ChatGPT to clarify the definition of negative log likelihood. ChatGPT breaks down the query and provides a detailed explanation. You can pose your own question and receive a response from ChatGPT. It is evident that logarithms play a role in the calculation of NLL. Next, we pass the logits L through a softmax function, then use the PyTorch NLL function, and finally check if the result aligns with the previous ones. The variable p represents the target, while the variables L1 to L4 represent the logit outputs. We apply the softmax function to the logit outputs to obtain normalized outputs Q1 to Q4. These normalized outputs are then passed through the PyTorch NLL function. Runtime error. Size mismatch. In our case, the function requires a two-dimensional input for the first argument. Therefore, we reshape each probability distribution before trying the function again. This time it is successful, but the result does not match the previous ones. When we apply the logarithm to the probability distributions, the results align with the previous ones. The question arises, what does the NLL loss function do? Let's examine the log probabilities and compare them with the values of cross-entropy. In our case, the NLL_loss function does not use a logarithm to compute the result. Instead, it selects the value of the predicted tensor based on the index in the target tensor and reverses the sign from negative to positive. Log_softmax is a computationally efficient and numerically stable function that is mathematically equivalent to taking the logarithm of the softmax function applied to a given input x. We can stack the inputs into a batch of 4 samples and calculate the cross-entropy as the average. The NN.NLL loss result is calculated without a log, which may be confusing. This understanding is crucial for grasping neural network principles, as we will use various examples to illustrate how neural networks operate. Thanks for watching.